Okay, so in this chapter, we are going to talk about smooth varieties, and this continues the study of varieties locally at a point. And so here the big picture is that X is a variety and A is a point. Then we have defined, using the blow-ups, the cone CA of X. And this had some nice properties. So this was a cone, so it was somehow invariant under scaling in some affine space. And its dimension was exactly the codimension of X at the point A. And we saw in an exercise that it's cut out by the initial terms of the defining equations of X. But such a cone is a less nice object maybe than having just a linear space which approximates our variety, right? So in practice, at least when X is nice, we hope that we can just at any point A find this kind of tangent space at X. And this would describe the variety locally. And so to get this tangent space, we would hope that it should be cut out by the linear terms of the defining equations, not just the initial terms. And this is what we say in the first definition. So let's say X is a variety and A is an X. Then, well, the variety is always covered by these affine open subsets. So we can choose such an affine neighborhood. And then A maps to some point in this affine variety. And by maybe translating the affine variety by the translation with minus the point that we get, we can assume that actually we restrict to neighborhoods such that X is an affine variety and A is just the origin. So for now, you can also say, let's first define the tangent spaces in this situation here. And then later we're going to see that what we define here is independent of whatever choice of affine neighborhood and translation we take. So it will be intrinsic to the variety X itself. So for now, let's assume we are in this setting here. And when we define the tangent space at A, inside AN to just be cut out by the linear terms of all the generators of the ideal of X. And so, I mean, all these generators are polynomials, and then we just throw away the higher order terms. And then this F1 is just the combination of linear monomials. Note, since F is an IX and A, the origin is supposed to be inside X, we automatically know that the degree 0 part is 0, because if we plug in the origin, then we exactly get back the 0 part, and this should be 0. And so this linear term is the first term which has a chance to be non-zero. Okay. And so this thing cut out by all of these equations is called the tangent space of X at A. And at least in the example, we see that this indeed gives us the space that we hope. So for example, if X is the vanishing locus of this equation here, this is some kind of parabola like this. And then when we look at the tangent space at the origin, this should be this here. And from the equations, we should see we keep the linear terms in the defining equation here, and we throw away the quadratic term, and then we get y minus 2x. And this is indeed the tangent space at this point. Okay, so at least in this example, it exactly works. And so some remarks about this definition. First of all, a very nice thing is that if you recall for the cone at the point A, it was not just enough to take some generating set S of the ideal and then plug in and look at the initial terms there. But for the tangent space, this is actually a nicer property, because there it suffices to just take the linear terms of some generating set S. So we don't have to write down this a priori infinite vanishing set. We can just take a finite set of generators. And so for the proof, well, let's say you have two elements in this set S, and any point in the tangent space that we defined above, then, well, for these 2 points, we have that F plus G, the initial term, or the linear term of F plus G, is just the linear term of F plus the linear term of G. these both vanish. So we get 0. And then second of all, we have that when we multiply by an arbitrary polynomial h against this function f, and we compute the linear term, then we saw always if you get the degree 1 term, then you have the degree 0 term of the first factor times the degree 1 term of the second factor, plus vice versa. And then because f is in the ideal, we have f of 0 equals 0. And since x is in the tangent space, we also have this thing here being 0. And so this holds. And so what this means is if we start knowing that all of these f and g in S vanish at the point x, then also arbitrary sums of these things vanish, and arbitrary products with other elements also vanish there. And these two operations can exactly give us all of the elements in the ideal of X by definition, because this is the generating set. And so this shows that if you only know that that all of the F1s for F and S vanish, then you're automatically contained in the tangent space. And the other inclusion is even easier because this is cut out by more equations than this one here. And so this shows that it suffices to restrict to this generating set. The one word of caution is, in this case, it is important to take the full ideal of X and then possibly some generators. It's not enough to just take any ideal whose vanishing locus is X. Because you see here in a small example, inside A1, of course, it's true that the vanishing locus of X and the vanishing locus of X squared are the same. But if you then apply the construction on both sides, well, if you take the linear term of X, then this is still X. And so its vanishing locus is just the origin. And this is the correct vanishing locus for this ideal here, the ideal of the origin. On the other hand, if you take the linear term of X squared, then you just get 0. And the vanishing locus of 0 is all of A1. So it really matters that you take this radical ideal here and not maybe some other ideal with the same vanishing locus. Okay, just to keep in mind. And then the final notion, this compares the tangent space to the cone that we had before, because, well, the cone was cut out by the initial terms when f is in I of x. And the tangent space is cut out by the linear terms when f is in I of x. And so let's say f is in I of x and the linear term is not 0. Well, then it is the smallest degree part of f which doesn't vanish. And so the f1 and the f initial are the same. And so in this case, you see we get the same generator here, or the same equation cutting out things. The second option is sometimes maybe f is in I of x and f1 is 0. In this case, note that on the right, we don't impose any extra condition because it's just the condition 0 equals 0 on this side. Whereas on the left-hand side, the f initial might still be non-zero. So in the second case, we impose more conditions on the left than on the right. So we saw for these elements of I of x, either we impose the same condition on both sides, or we impose more conditions on this side, on the left side, than on the right. And so overall, this CA of x is cut out by at least as many equations as the TA of x. And so it is contained in here. And here this exercise tells us exactly that CA of x is described by this thing here. Okay? So the upshot of this short discussion is that CA of x is always contained in TA of x. So this CA of x is what is kind of union of cones and so on. This is always contained in this linear space. In particular, because of this containment, the dimension on here is always greater or equal to the dimension of CA of x, and we have seen the dimension of CA of x is exactly the codimension of x, of the point A inside x. So from this discussion, we get some inequality here. And we're going to see the nicest and most interesting cases when we have an equality here. Okay. And let's look at this in some more examples. So here are these three plane curves that we have seen before. And we had computed, and this is kind of in this darker gray, we had computed the cones at the origin. So somehow here, we just got the x-axis. Here we got these two diagonals. And in the third example, we again got just the x-axis. And now let's look at what is the tangent space. So in this case here, when we throw away the quadratic term, then we just get the vanishing locus of x2. This is again the x-axis. And so somehow in this case here, the two C0 and T0 of this variety agree. So this is the kind of nice case. And this corresponds to the fact that this is a nice variety around the origin. Whereas in these two cases, we saw, well, these points are a bit suspect. I mean, these points are probably not such nice points inside the variety. And we can see this from the tangent space because, well, here, if we take the linear term, then there's no linear term at all. So we just get the vanishing locus of 0. So this is the entire space, A2. So, and actually, we could have seen this differently because this tangent space is the linear space, and it contains the C0, right? So somehow in this case, it's a linear space. It must contain these two diagonal and anti-diagonal. And this automatically forces it to be all of A2. Because these, for example, these 2 points here are linearly independent. They form a basis of A2. And in the third case, we still see, if we take the linear terms of this equation, then we get 0. So somehow, again, the tangent space in light gray is everything, is all of A2. And this is despite the fact that the C0 of x3 is a linear space of dimension 1. So it's not always the case that the tangent space is the smallest linear space containing C0. You still just have to plug in all of these generators of the equation, take the linear part, and take the vanishing set. Okay, so we see here, at least in this example, that this nice point here and the two maybe not so nice points here can be distinguished by comparing the cones at this point and the tangent space. And this we're going to make more precise very soon.